Welcome to other boundary conditions and the heat equation. So recall, in the case where both ends were held at 0, we were looking at the problem. The model was first partial with respect to t of u is equal to a squared times the second partial with respect to x of u. We had u of x0 was f of x. And we had u of 0t equals u of lt equals 0. We wound up getting that u of xt is equal to the sum from n equals 1 to infinity of c sub n times e to the negative a n pi over L, the entire fraction squared, times t, times sine of n pi over Lx. Again, where our Cn were equal to 2 over L times the definite integral from 0 to L of f of x times sine of n pi over Lx dx. We're now going to modify our boundary conditions. So instead of looking at both ends held at 0, let's now look at the case where both ends are insulated. So what this means is that the partial with respect to x of u is equal to 0 on the boundaries. So if both ends are insulated, then this translates to the partial with respect to x of u evaluated at 0t is equal to 0, is also equal to the partial with respect to x evaluated at lt. We also have, again, our original equations. So we have the partial with respect to t of u is equal to a squared times the second partial with respect to x of u. And again, we have u of x0 equaling f of x. In the separation of variables process, we wind up with x double prime plus lambda x equaling 0 with boundary conditions x prime of 0 equals x prime of L, both equal 0. And of course, this leads to the cosine. And so this leads to xn being cosine of n pi over Lx. And we also get an x naught equaling 1. So we wind up getting for our solution, u of xt is equal to a naught. Actually, I'm going to stick with c naught. We'll do a naught. A naught plus the sum from n equals 1 to infinity of a sub n times e to the negative n pi a or a n pi over L, entire fraction squared t times cosine of n pi over L times x. Here, if we plug in t equals 0, we wind up just getting the cosine, Fourier cosine series for f. And our A naught is just 1 over L times the definite integral from 0 to L of f of x dx. Our A sub n is 2 over L times the definite integral from 0 to L of f of x times cosine n pi over Lx dx. Next up, let's look at the first end is held at 0 degrees and the other end is insulated. The first end being held at 0 degrees tells us that u of 0t is equal to 0. The other end being insulated, this is the first partial with respect to x, evaluated at Lt is equal to 0. Again, we still have that the first partial with respect to t is equal to a squared times the second partial with respect to x. We also still have that u of x0 is equal to f of x. So note in this case, separation of variables gives the equation x double prime plus lambda x equals 0 with boundary conditions. X of 0 is equal to 0 is x prime of L. This has solutions xn equaling sine of 2n minus 1 pi over 2L times x. And so again, our t component of our separation of variables is still the same formula. Our lambda is now though our 2n minus 1 over pi, or 2n minus 1 times pi over 2L. And we wind up getting the solution. So we wind up getting that u of xt is equal to the sum from n equals 1 to infinity, c sub n times e to the negative a times 2n minus 1 times pi over 2L whole thing squared t times, that's all in the exponent. I'm going to shift the c, n, and e down a little just so that's more obvious. And then times sine of 2n minus 1 pi over 2L times x. In this case, our c sub n are 2 over L times the definite integral from 0 to L of f of x times sine of 2n minus 1 pi over 2L times x and dx. Finally, we'll look at the case where the first end is insulated and the other end is held at 0. So the first end being insulated means that that first partial with respect to x of u evaluated at 0t is equal to 0. The other end held at 0 just tells us that u of Lt is also equal to 0. We still have the same partial differential equation first partial with respect to t of u is equal to a squared times the second partial with respect to x. And we will still have that u of x0 is equal to f of x. So again, the only thing we're changing is our boundary conditions here. Again, note separation of variables results in x double prime plus lambda x equaling 0 with boundary conditions x prime of 0 equals 0 equals x of L. So this gives us x sub n of the form cosine of 2n minus 1 times pi all over 2L times x. And so we wind up getting the mixed cosine series, essentially. So we wind up getting u of xt is equal to the sum from n equals 1 to infinity of c sub n times e to the negative. Again, our lambdas here are 2n minus 1 times pi over 2L whole thing squared. So we'll have a times 2n minus 1 times pi all over 2L, that entire fraction squared, then times t, all in that exponent. And then we multiply by cosine of 2n minus 1 times pi over 2L times x. And our c sub n's are the same c sub n's from our mixed cosine series. We wind up with 2 over L times the definite integral from 0 to L of f of x cosine of 2n minus 1 pi over 2L x and dx. So these are essentially the 4 cases we'll deal with where we have homogeneous boundary conditions, 0 boundary conditions, and the rod itself is insulated, so heat's just transferring within the rod and out the ends, possibly. So again, this is our the 4 possible cases we might wind up with. Note that we have used all cases except the case where we set x of L equal to x of negative L and set x prime of L equal to x prime of negative L. But we have used the other 4 cases we discussed in chapter 11 to solve these 4 different boundary value situations.